So as far as thermodynamics are concerned, work doesn't really get talked about that much. We're going to spend this video looking at the calculations involved in work and focusing just on quantifying work, and then we're pretty much going to ignore it from here on out. So work is defined as a force acting through a distance. And here's the equation. So work is equal to force times distance. Now, you know that work is measured with the units of joules. Force is measured with the units of newtons. So if we take joules, that will be equal to newtons times distance measured in meters. So a newton meter is equal to a joule, and that's how we can calculate work. So if we have a reaction taking place in this container, so we're going to say here's our reaction, it's in this container, and this reaction is going to produce a gas. Now the gas that is produced by this reaction is going to push up on that container, on the outside of that container, causing it to move a certain amount of distance. Now when it pushes up, it has to push against the force, the atmospheric pressure, the force of the atmospheric pressure. So we call this pressure volume work, and this occurs when a force is caused by a volume change against an external pressure. So this is what we would see in terms of work in a chemical, or work being caused by a chemical reaction. So we have, here's our work formula. We have work equals force times distance. This is the one that physicists use to calculate the amount of work. We're going to apply it and kind of transform it into a more chemistry application. So just to remind you that work is equal to force times distance, and pressure is equal to force divided by area. Remember that pressure equation from when we talked about gases? That comes back here. Now what we're going to do here is we're going to solve for the force. So force equals pressure times area, and we're going to plug that into this equation. So then what we end up with is work is equal to pressure times area times distance. We're going somewhere with this. We're going to bring it back to this cylinder in just a second. So the work done is equal to the pressure times the area times the distance. Now, if you take a look at the area, because we're always going to be dealing with a geometric shape that our chemical reaction will participate in, the area is going to equal, or the area times the distance is going to equal the volume. So we're going to kind of wrap this up into a chemistry definition. Work is equal to negative the pressure, the external pressure, because the pressure is pushing down on this container, times the change in volume of the container. And now we have to look at our units very carefully here. Pressure has a unit of atmospheres, and volume has a unit of liters. And it turns out that 1 atmosphere liter is equal to 101.3 joules. So let's do a couple practice problems with this. If we have a gas inside of a piston, and the gas is heated, and it causes the piston head to move 9.0 centimeters against an external pressure of 5 atmospheres. Now the radius of the piston is 2 centimeters. How much work does the piston do? So here's our work equation. Work equals negative the pressure of the external force times the change in volume. So the pressure, the external pressure, is 5 atmospheres. So we're going to take negative 5.0 atmospheres and multiply that by the change in volume. Well, we have to do some calculations to determine that delta V. We have the piston head moving 9 centimeters, that's our distance, and the radius of the piston is 2.0 centimeters. So to calculate the area there, we need to use some geometry. So we have area times distance. Now the area of that piston head is pi r squared. That's what we calculate the area of a circle. By the way, a piston head is circular, so we use pi r squared. It has a radius. And so pi times 2.0 centimeters squared. And then we're going to multiply our distance, the distance that it pushes against the atmosphere, so 9.0 centimeters. We get 113 centimeters cubed. We still don't have units of liters yet. We want units of liters. Just as a reminder, 113 cubic centimeters is equal to 113 milliliters. So we have 0.113 liters as our change in volume. So if we multiply this all out, we get negative 5 atmospheres times 0.113 liters, and we get negative 0.565 atmosphere liters or liter atmospheres. Now remember, 1 liter atmosphere is equal to 101.3 joules. So we're going to do a little dimensional analysis. We're going to cancel out liter atmospheres and turn it into joules, because we want to calculate work in joules, not liter atmospheres. So 1 liter atmosphere is equal to 101.3 joules. So we multiply that by our 0.565 liter atmospheres, and we get negative 57 joules. So a negative 57 joules. That means overall work is being done to the surroundings. The system is doing work to the surroundings, so it's losing that energy. So it's a negative value. We can do work on the air in a bicycle pump by pushing it down. The gas inside has a volume of 3.00 liters. If we apply a constant external pressure of 1.10 atmospheres and push down on the handle of this bicycle pump until the gas is compressed to a volume of 2.50 liters, how much work did we do on the gas? So we're going to set this up just like we set up all of our other problems with work. Work is equal to negative the external pressure, the pressure pushing in on the system, times the change in volume. So the pressure exerted on the system is negative 1.10 atmospheres. So we're pushing, there's 1.10 atmospheres pushing onto the system. We're going to multiply that by the change in volume. But first we have to calculate what the change in volume is. So we're going to use that delta V. Delta V is equal to the final volume minus the initial volume. So the final volume is 2.50 liters. The initial is 3.00 liters. So 2.5 minus 3.0 liters is equal to negative 0.50 liters. So I take negative 1.10 atmospheres and multiply that by negative 0.50 liters. And then what I'm going to end up with is a positive number. And that should make sense because you're doing work on the system. You are compressing the gas that is in the system. So you're doing work on the system. So we get 0.55 liter atmospheres. What we're going to do then is turn this into a dimensional analysis problem, converting liter atmospheres to joules. So 1 liter atmosphere is equal to 101.3 joules. So I'm gonna now I'm able to cancel out my liter atmospheres and turn it into joules. So 0.55 liter atmospheres times 101.3 joules is 56 joules. Remember, this is a positive number because we are doing work on the system. We're pushing down the gas, we're compressing the gas in the system, means we're doing work on the system.